For this unit, we're going to be looking at adding, subtracting, multiplying, dividing, and solving problems involving radicals. So this is the extension on our 10C unit. So we're going to start with a little bit of a review. First, if I said that 7 times 7 is equal to 49, the square root of 49 would be 7. Also, negative 7 times negative 7 would equal 49, which means that another possible square root is going to be negative 7. The number 49 has two square roots, a positive one and a negative one. Just like when we're dealing with our quadratic formula, we always say positive or negative, whatever it happens to be. The positive one is the principal square root. The negative one is the secondary square root. Now, to indicate them, I would have to state whether it's positive or negative in the coefficient of the square root, because remember, we can't take the square root of a negative, so it can't be inside of that sign. Every positive number has two possible square roots, the principal square root and a secondary square root. Negative numbers don't have square roots in the real number system because it's not possible to get two numbers multiplied by themselves that will wind up being negative. If it's a negative times a negative, it will be positive. If it's positive times a positive, it will still be a positive. Now, if I'm looking at cube roots, well, 3 times 3 times 3 is 27, so the cube root of 27 is 3. Negative 3 times negative 3 times negative 3 is going to be, and there's a typo here, it's actually negative 27, which means the cube root of negative 27 is negative 3. Because when I multiply a number an odd number of times, 3, 5, 7, however many it happens to be, it will wind up reverting back to its original sign. A negative times a negative times a negative is still negative. Positive times positive times positive is still positive. So cube roots, fifth roots, seventh roots, they only actually have one root. They don't have two possible roots. Now, you don't have to be able to do this without a calculator. You can always use your calculator, but if you know, the square root of 64 is 8. The square root of negative 64 is not real. There is no real answer for that. The negative square root of 64 is going to be negative 8. Just take whatever the square root of 64 is and then flip the sign. If I have the cube root of 64, that's going to be 4. The cube root of negative 64 actually does work. That is negative 4. And if I take the cube root of 64, which is 4, and then multiply it by a negative 1 on the outside, it's still just going to be negative 4. If I put in the cube root of 729, which depending on your calculator is either going to be under the math button, where there's going to be roots that are other than square roots, or if you're on a Casio, you can do the shift X root button. Cube root of 729 is going to be 9. Square root of 196 is 14. And if I take the cube root of 512 over 343, that's going to be the same as the cube root of 512 over the cube root of 343, which is the same as 8 over 7. Now remember, if I take the square root of something that is not a perfect square, I'm going to wind up with an irrational number that's going to go on and on forever with no repeating pattern. So if I just want this to the nearest hundredth, well, this would be 7.21. And the cube root of 71 is going to be approximately 4.14. These square roots of non-perfect squares or cube roots of non-perfect cubes are going to be our radicals, where radicals can be simplified with a coefficient on the outside potentially, and they're made up of 3 parts. They have the index, which says what root we're taking. There is the radical symbol, and the radicand on the inside is the number that we're taking, the square root, cube root, whatever it happens to be of. The entire thing all put together is a radical. Anytime the index is not written, we should already know that's a square root or there's an imaginary 2. So anytime we have something like this, there's actually just a imaginary 2 in the index there. So if I'm identifying the index in the radicand, well, this has an index of 3 and a radicand of 123. Here it doesn't say anything, so it has an index of 2 and a radicand of 77. And here I have an index here of 3 and a radicand of negative 1/2. That 8 on the outside is just a coefficient. Now, I can multiply or divide radicals, which we should already know. If I said the square root of 25, that's going to give me 5 times the square root of 16 times 4, that's going to give me 20. If I take 25 times 16, that's going to be the square root of 400, which also happens to be 20. So these are equivalent. The square root of 25 divided by the square root of 16 gives me 1.25. When I divide 25 by 16 and then take the square root, I also get 1.25. This is equal to. The square root of 25 plus the square root of 16 gives me 9. It would be the same as 5 plus 4. If I take 25 plus 16, or take the square root of 41, I get approximately 6.40. This is not equal to. Or if I take 5 minus 4, or the square root of 25 minus the square root of 16, that's going to give me 1. If I take the square root of 25 minus 16, or the square root of 9, that would give me 3. This is also not equal to. Which means that the product or quotient, so the multiplication or division of radicals, is always going to be equal to the product or quotient of the two numbers inside of the radicand. But I can't say the same for adding or subtracting. When you add or subtract, it is not equivalent. It's only when you multiply or divide. So I can say that root x times root y is the same as root xy, or the square root of x over the square root of y is the same as the square root of x over y. So here, if I said the square root of 6 times the square root of 3 is equal to 18, well, 6 times 3 is also equal to 18. This is true. Remember, it does not work the same way when I'm adding or subtracting. This is false. And if I take the square root of 60 divided by the square root of 6, well, 60 divided by 6 would be 10. This is also true because it works for multiplying or dividing. Now, if I'm using a calculator to approximate to 5 decimal places what each of these are, if I put the square root of 48 in my calculator, I get 6.92820. Conveniently enough, if I take 2 times the square root of 12, I also get 6.92820, and 4 times the square root of 3 also gives me 6.92820. What do you notice about the answers? Well, they're all the same. So if I use the rule where I know that the square root of x times y is the same as the square root of x times the square root of y, well, all we do is we can say, well, 48 I can split up into 4 times 12, to the factors, which would be the same as the square root of 4 times the square root of 12. The square root of 4 is just 2. I can actually solve that times the square root of 12. And that's how I got from the square root of 48 to this one. At the same rate, if I take two other factors, 16 and 3, that's going to be the square root of 16 times the square root of 3, or 4 times the square root of 3. And that's how I got to this. this answer. So that's why they're all equivalent. If I have the square root of 48 where I have no coefficient on the side, it's an entire radical. If I said 2 root 24 or 4 root 6, those are going to be mixed radicals. That just means that there's a coefficient on the outside that the radical is being multiplied by. If I'm converting from entire radicals to mixed radicals, there's two ways you can do this. One is if you know what all the perfect squares are, you can factor out the largest perfect square that can get divided out of here. 20 is only divisible by the perfect square of 4. So I'd say that's the square root of 4 times the square root of 5, or 2 times the square root of 5. This would be the same as 2 root 5. If you don't like this method, you can always use the factoring tree method as well. If I take 20 and I do prime factorization, I'm going to divide by 2 until I can't anymore, 2 times 10, and 2 times 5. And now I have the prime numbers that make up 20, 2 times 2 times 5. If I'm looking for a square root, I'm looking for 2 of the same number, or pairs. If I find a pair, one of those pairs can make it outside the radical. Anything that does not have a pair has to stay inside the radical. And I get the same answer, that 2 root 5. There's a number of students who find this more convenient because they don't have to memorize the perfect squares, perfect cubes, perfect fourths.